Good morning, everybody. Welcome back to this next week. So let's shift our focus now for the study of the catalysts and the catalytic reactions. So starting this week, we will move on to this new topic. So let me start sharing my screen with you. And let's start the presentation. Okay, some important announcements. We will have in-class assignment on Friday. And as we agreed at the beginning of the semester, we also will have a makeup exam next Monday. Therefore, no lecture next Monday. The makeup exam will replace exam number 2, and I will ask again the questions involving what was covered in the exam number 2. If you want to take the exam, you are welcome to do it. If you don't want to take the makeup exam, it will not hurt you as well. Okay. Okay, so let's start with catalysis. So I will split this lecture in 3 different parts. First one, I will talk about catalysts. Second one, I will show you the catalytic cycle. And the third and last part, we will talk about the types of reactions involved in catalytic cycles. Okay. So let's start with topic number 1, definition of a catalyst. Catalyst is a substance that alters the rate of a reaction without changing the position of the equilibrium. Okay, so the way the catalyst alters the rate of the reaction or of a given reaction is by decreasing the activation energy, as you can see here in this energy diagram. Okay, so black line is the reaction in the absence of catalyst. So the activation energy is the energy from this point all the way to the top of the curve. However, in the presence of the catalyst, there is a new path for the reaction to follow. And this new path is represented by this light red curve. So as you can see here, now there is the formation of an intermediate, then the reaction proceeds and reach the products. As you can see, the energy of the reactants and the products is the same in both cases. So there is no change in any of the energetics of reactants and products. However, the activation energy is much lower compared in the absence of the catalyst. And that's why a catalyst increases the rate of a reaction, okay? And important thing to note, the catalyst does not affect the concentration of the species in the equilibrium. It only affects how fast it is reached. Okay, some points to consider when designing a catalyst or choosing a catalyst for a given reaction. We must pay attention here in 4 different points. The first one is the concentration of catalyst required. Ideally, we want to use low concentration of catalyst, okay? So just a small amount of catalyst and that would yield the highest amount of product. Second point to be considered, the catalytic turnover number, or TON, and turnover frequency, TOF. TON is defined as the number of moles of product produced per mole of catalyst. Okay, so TON is the number of moles of product produced per mole of catalyst. Okay, ideally, you want to produce a lot of product with a small amount of catalyst. And turnover frequency, or TOF, is defined as the turnover number over time. Okay? So just a different number that means basically the same thing. And ideally, what we look for in a catalyst is a high TON and high TOF. Third point, the selectivity of the catalyst to the desired product. Okay, so if a reaction produces more than one product, you will need an extra purification step, so that's not ideal. So ideally, your catalyst will first give a high amount of product, and second, be selective towards the formation of only one product. Okay, that saves time and money with following separation steps. And fourth point is how often the catalyst needs renewing. So ideally, you want to use the catalyst more than one time. So ideally, what we look for is low maintenance. Okay, so the catalyst can be recycled for several cycles. Okay, so now let's move on. Let's talk about types of catalyst. So basically two different types, heterogeneous and homogeneous. Heterogeneous catalyst is when the catalyst is in a different phase from the components of the reaction. Advantages to that, pretty easy to separate catalyst from the reaction. Disadvantage or disadvantages, the reaction only happens at the interface between the catalyst and the reaction. Okay. On the other hand, homogeneous catalyst is when the catalyst is in the same phase as the components of the reaction. Okay. The advantage is that there is higher interface between catalyst and reaction, but the disadvantage is that it's a little harder to separate catalyst from the reaction at the end. Okay, so I showed you so far the definition of a catalyst, the 4 characteristics that we should look for in a good catalyst, types of catalyst. So now let me show you what's a catalytic cycle. So the catalytic cycle consists of a series of reactions often reversible, that form a closed loop. Attention, the catalyst must be regenerated at the end of the cycle. Okay, so let me show you this catalytic cycle. So basically here we are feeding the system with CH2, CH2, and getting as the product CH3CHO. Okay, so conversion between a double bond into an aldehyde compound or aldehyde group. The catalyst for this reaction is tetrachloro palladiate 2 or PDCl4. So the reaction proceeds. We have here a lot of steps all the way to the end, and then at the end the catalyst is regenerated and can go again in another cycle. Okay, so that's what we are looking for. So catalyst always shows up as reagent in the first step and as the product in the very last step. So all the way here. And the catalytic cycle is all this cycle over here, a closed loop, and the catalyst being regenerated here at the end. Okay, very good. So types of reaction that we are going to cover in this course. Two different types. First one, reactions involving gain or loss of ligands. So we have four types here. First one, ligand dissociation and substitution. Second one, oxidative addition. Third one, reductive elimination. And fourth one, nucleophilic displacement. Okay, so that's what we are going to discuss today. And the second type that we are going to leave for Wednesday is reactions involving modification of ligands. Again, four different kinds. First one is insertion. Third one is carbonyl insertion or alkyl migration. Third one is hydride elimination. And fourth, abstraction. Okay, so focus for today is in the first one. So let's move on and discuss each of the different kinds of reactions involving gain or loss of ligands. Okay, so let me show you the first one. So let's talk about ligand dissociation and substitution. This is a simple substitution reaction, okay? The first step consists of losing one of the ligands, and the second one is the addition of a different ligand. Usually, the mechanism of this substitution is by dissociation. Okay, so let's take as an example here the reaction of pentacarbonyl iron 0. So pentacarbonyl iron 0 is 18 electron species. So we are going to review a little bit later how to get the 18 electron species and how to make sure a compound obeys the 18 electron rule. Okay, so for now, pentacarbonyl iron 0 is an 18 electron species, so it is a stable compound. However, in the presence of light in the UV range, uh, one of the bonds between carbonyl and iron is broken. So there is a loss of one carbonyl ligand. As a consequence, this intermediate has 16 electrons, therefore is unstable, therefore is reactive, and it's going to react with a ligand L. So this ligand L provides electrons to the system, forming a 18 electron species that is stable. Okay? So always in a reaction, there is something that destabilizes the system, and that's the motivation for the system to react with something else, forming a new compound. Okay. Ligand dissociation and substitution. First step is losing one ligand or more, and then second step is adding or the addition of a different ligand. And that's how the reaction proceeds. Okay. All right, let's move on to the second kind that I would like to show you today. So the second one is called oxidative addition. In this kind of reaction, there is increase in both oxidation state and coordination number of the metal. Attention, increase in both oxidation state and coordination number of the metal. So let's see a generic equation here, starting from a Ml4 complex, and we are going to react with AA. Okay. So after the reaction, there is the formation of this complex. Now we have M, L, 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 and A were added to the coordination sphere. Okay. Oxidative addition usually starts with a square planar complex. Why does it start with a square planar complex? Because this kind of complex has low coordination number, equals to 4. Therefore, we can add ligands to expand the coordination number and usually forming an octahedral species. Okay? Always pay attention with that. Okay? And when you have oxidative addition, both atoms from the reagent are going to be inserted in the coordination sphere. That's one of the conditions for the oxidative addition. Ligands such as halides, hydrogen atom, and organic radicals are treated as anions. Okay, pay attention on that. Halides, hydrogen atom, and organic radicals are anions. Okay, so when we have Chlorine coordinated is coordinated as chloride or bromide or iodide. Hydrogen coordinated, this indicates that's being coordinated as hydride. Okay, there is a negative charge there, and you have to take that into account. Okay, so I would like to show you an example of oxidative addition. So let's make sure we understand the concept, and let's make sure you pay attention to this detail here, which is super important. Okay, so let's start here with a square planar complex. So we have iridium here at the center. So first thing I would like to do is to calculate or to get the oxidation number of iridium, or the oxidation state. Okay, so carbonyl, we have carbonyl, we have a phosphine here, same phosphine trans, and we have a chloroligand. Carbonyl, phosphine are neutral, or oxidation state is equals to 0, and chloro, when it's coordinated, is 1 minus. The global charge of the complex is 0, so that means iridium is 1 plus. Okay, the oxidation state for iridium in the starting complex is 1 plus. Now let's react this complex with hydrogen gas. So when we do that in special conditions, there is addition of both atoms to the coordination sphere. And now what I would like to do is to check the oxidation state of iridium. So we are going to do the same thing. Remember, carbonyl and phosphine, they are neutral molecules, therefore the oxidation state is 0. Chloro, when it's coordinated, is -1. And hydrogen, when it's coordinated, is -1 as well. So that gives us a total of 1, 2, 3 minus. If the net charge of the complex is 0, that means the oxidation state of the iridium is 3 plus. Okay? Now let's take an overall look at the reaction. So we started with a complex that has coordination number equals to 4. And at the end, the coordination number increased to 6. So that's an indication of oxidative addition. This indication is going to be confirmed by the increase in the oxidation state of the iridium going from 1 plus to 3 plus. Okay? So that's an example of oxidative addition. And that's usually the beginning of the catalytic cycle. Okay, if we have oxidative addition, we must have the opposite to that, which is reductive elimination. In this kind of reaction, there is decrease in both oxidation state and coordination number of the metal. So it's basically the opposite of oxidative addition, guys. So example here, let's start with this complex. Coordination number equals to 6, metal at the center, 4 ligands and 4L ligands and 2A ligands. These 2A ligands, for special reasons, can be eliminated from the coordination sphere as AA, and that gives us the complex ML4. Okay, so reduction or decrease of the coordination number, here going from 6 to 4, and there must be decrease in the oxidation state of the metal. Remember, ligands such as halides, hydrogen atom, and organic radicals are treated as anions. Okay, remember that. So let's do an example to make sure you understand how to identify a reductive elimination reaction. Okay, so let's start with a cobalt complex, coordination number equals to 6, octahedral geometry right here, and we can force this hydrogen and this acyl group to leave as an aldehyde, and we have the formation of a cobalt complex with coordination number equals to 4. Okay, so just looking at the reaction, there is a decrease in the coordination number from 6 to 4. That's a very strong indication of reductive elimination. So we will confirm that by verifying the oxidation state of the cobalt. If there is a decrease, then it's reductive elimination. Okay, so same process here. Carbonyls are neutral molecules, therefore oxidation state is 0. Hydrogen, when is directly coordinated to the metal, is counted as 1-, and any sort of organic radicals, when are coordinated to the metal, are considered 1- as well. So for the starting complex, we have 0, 0, 0, 1-, 1-, and 1-. So that is a total of 3-. If the whole complex is neutral, the oxidation state of the cobalt must be 3+. Okay. Now let's do the same thing for the complex that was generated after the reaction. Again, carbonyl ligands are neutral, and hydrogen, when it's bonded, is 1-. So that's what we have for the ligands, 0, 0, 0, and 1-. So that's 1- in total for the ligands. If the net charge of the complex is 0, that means the oxidation state of the cobalt is 1+. So now let's take a look at the reaction. First thing, there was a decrease in the coordination number from 6 to 4, and also a decrease in the oxidation state from 3 plus to 1 plus. Therefore, this is a reductive elimination. When we have reductive elimination, usually the product is going to be an RH, RR, RX, or HH type of compound. Here R and R prime are alkyl or aryl groups, and X is a halogen. Okay. I hope it is clear what is a reductive elimination kind of reaction and how you identify that. Okay. All right. Let's move on to the last kind of reaction that I would like to show you today. And it's a pretty simple one, nucleophilic displacement, very similar to the organic chemistry. In this kind of reaction, the metal complexes, especially those carrying negative charges, behave as nucleophiles in displacement reactions. So let's take this reaction as our example. So we have here a square planar complex that has molybdenum as the metal, 3 carbonyl ligands, and a cyclopentadienyl ligand as well. Okay. Net charge of the complex is 1 minus, coordination number equals to 4. That means it can act as nucleophile and can expand the coordination sphere. So it's like this pair of electrons attacks here the H3Ci, kicks out the iodide and coordinates the CH3. Okay, very similar to the oxidative addition. However, only part of the reagent is added, therefore it's called nucleophilic displacement. All right, similar to the organic chemistry. Imagine this as a nucleophile that's going to attack this group. There is a break in this bond here, forming iodide and a complex with coordination number equals to 5. Okay, so nucleophilic displacement. Okay, I think that's a good point to stop for today. On Wednesday, we will see the other kind of reaction that may happen in catalysis, in catalytic cycles, and then next week maybe we can move on to analyzing some catalytic cycles from literature. Okay, so if you did not understand anything or a specific point of the lecture, let me know. Do not leave for the last minute because it will accumulate and you will be overwhelmed. Okay, so let's try to keep it up, guys. Okay, almost the end. Okay, I will see you on Wednesday. Hope you have a good weekend. Sorry, a good week.